welcome to the Math Kangaroo stream for today. Today we are doing grades 9 and 10 from, I believe, 2021. My co-host today, Anshul, is a very, very cool person. He did USFO this year, which is the Physics Olympiad. He is in his 7th year of Math Kangaroo, so he is well qualified for this stream. And interestingly, he has eaten the same lunch for 7 years. What lunch is deserving of this?
It's pasta, which I eat like pretty much every single year. But I'll introduce you now. This is my co-host Alina. She did MOP 2022, which I think it's camp, but I don't know. And then she participated 9 years in Math Kangaroo, which is 2 years more than me. And then she can tell if it's raining either by her head hurting or by looking outside.
It's a very admirable skill.
Yeah.
All right. I think we can get started with our questions for today. I see a hi in chat. If you are interested in having your answers or questions or clever comments displayed right down here on my screen, then you should send comments to Chat Relay, and then they will go through our wonderful mod panel. And if they're really, really cool, they will show up down here. And if they're really, really, really cool, then they will also get a little star next to them. So if you'd like to contribute, that would be absolutely wonderful. And with that, I think we should get started. All right, question number 3. A certain park is shaped like an equilateral triangle. A cat wants to walk along one of the 3 indicated paths, bigger lines, from the upper corner to the lower right corner. The lengths of the paths are P, Q, and R as shown. Which of the following statements about the lengths of the paths is true? Okay. Interesting. I mean, okay, one thing I see right away about the paths is that we have an equilateral triangle in each one of them. So what this tells me is that, for example, this segment on R here should be the same length as this segment here, because we have an isosceles trapezoid. So we're assuming that these sort of like horizontal bases are parallel to each other. And since we have an equilateral triangle, we have angles like this are equivalent to each other, which means we get an isosceles trapezoid. So what this means is that if we take the right side, we should get the same thing as the left side. So this makes me think that I can essentially not consider the slanty parts of the paths, because for each one of these 3 paths, I can just take all of the slanty parts on the right and shift them over to the left. And then because I make my way all the way from the top down and I don't go back up, this means that I'll just have a complete sort of like line down, complete side on each one of these. So this tells me that I don't have to consider the slanty parts, I should only be considering the horizontal parts. And of comparing horizontal parts, well, P, Q, and R all have this bottom segment here. So that tells me that I shouldn't consider that either, which means we only have a couple more trivial lengths to consider. So for example, we have P, does that show up? Ooh, okay. P and R have this common length, and then we have P and Q have this length, and then Q and R have this length in common. And actually, it's not that bad to compare them because we can tell which ones are shorter and which ones are longer. So I think this is just as easy as just looking at the picture and seeing which ones are longer. So obviously P is the combination of the 2 shortest paths. We can see that it's the topmost and then the middle path. And because the triangle gets narrower as it goes up, this means that this should be the shortest path length. And then we see in Q, we have the middle and the bottom length, which means that this should be the longest path because we're taking all of the ones that are concentrated at the bottom where the triangle is the widest. So Q should be the longest. And then R is taking the top and the bottom path, which should leave it somewhere in between P and Q. So I'm going to be looking for an answer that has P is less than R is less than Q, or the other way. Oh, which is answer choice B. Yeah.
I think we're gonna start on problem 6 now, which I think the next third one. I don't know. So this problem, you basically have this type of like hexagon shape, and then you have like the rhombuses inside, and all you have to do is like pretty much we can like split this up into like triangle shapes. You feel me? Like you just say cut it up like this, like that, and then like a nice thing is that this part right here is equal to that part. I'm bad at drawing, but yeah, these two parts are equal, and then these two parts are equal, and then you cut this in half. These two parts are equal. Cut that. Feel like I'm bad drawing. And then so these are equal. So we have this like exterior part. So what we do next is we take this sum. So we split this down the middle, right? So this interior part, which is to be 6 times 5 over 2, which would just give us what's it called? 15, right? And then we also know that this outside part is 15, so we have another 15 on top. And then finally, we have this like outside part, which we know is equal to the outside part of the rhombus shape, which is another 15. And then we just add these all up, 15, 15, 15, we get a 45. Yeah, and then Skylar also got the answer, 45 as well.
Oh, that's a really cool approach. I didn't consider it. And just in case it was like not incredibly visible, I think like the main point, right, was that you like split all of these rhombi into like we split them down the middle to make these equilateral triangles. And then like we have that this like third of the equilateral triangle is an actual third because like they're all congruent. Oh, I see an alternate suggestion in chat as well from Alex Yu to split the hexagon into 6, and then by extraction, the rhombi are 2/3 of the equilateral triangle. Oh, that's exactly what it was. Yeah, very cool. I love the use
it's
of
low-key a better solution. Oh, my bad. Yeah, it's low-key like a way better solution. I don't know. I'm just being dumb. But yeah, you could just make a...
Amazing. All right, so moving on to the next problem. Ali drew 3 triangles on a grid. Exactly 2 of them have the same area, exactly 2 of them are isosceles, and exactly 2 are right triangles. 2 of the triangles are shown. Which could be the third one? Okay, so we have exactly 2 are isosceles, exactly 2 are right triangles, and 2 have the same area. Well, right away we can tell that these are the 2 right triangles. That means our other triangle shouldn't be a right triangle. So that immediately eliminates option E. I should not use green for eliminating. That's counterintuitive. No E. Okay, what else? 2 of them are isosceles. And of these, well, this one has side lengths 4 and 5, and the other one has 4 and 4. So we have exactly 1 isosceles triangle. So this means that the third triangle should also be isosceles. So what this means is that we can eliminate, looks like option B is not isosceles, and if we do the Pythagorean theorem to calculate like this side and the other slant side, we'll see that they're different. So it can't be B. And then C looks pretty isosceles, D looks pretty isosceles, A looks pretty scalene, so we can eliminate A as well. Then the last condition is we have to look at areas. And we can see that since this triangle has an area of 10 and this triangle has an area of 8, they have different areas, so we need our third triangle to have the same area as one of these 2 triangles. And so if we look at C and D, this one has a base of 4 and a height. We can draw this sort of vertical line, which I guess is horizontal here, but this works as an altitude. This looks like 6 units. So you would get 4 times 6 over 2, which is not equal to 4 times 4 or 4 times 5 over 2. And this suggests that the answer is D, but we can double check that as well. Here we have a base length of 4 and a vertical height also of 4, which matches up with this triangle up top. So that suggests that the answer should be D. Yeah.
All right. Well, so the next problem I think will be problem 12, which is it's just a dude walking up 8 steps, and you can either go 1 or 2 at a time, and then and he has to skip the 6 steps. So how many ways to get to the top? And when we think about that, if we have like the 6 steps, we can just write them all out: 1, 2, 3, 4, 5, 8. And if he can't go on the 6th step, he will have to go a 2-step right here. So from 5 to 7. And if he's at 7, he obviously has to go to 8. So right now our problem is just how to get from 1, 2, 3, 4, 5, and you can either do 2 or 1 steps. So like you can just do like different cases where we first have 2 steps, two steps I mean, and then we would have 2 here, and there would be you can either be in the 1 skip can be in the 3 spot, the 1 spot, the 5 spot. So we get 3 of those. Then we have the 2 spot. Wait. Yeah, I'm doing it all. Then we can have the other one. So we have another 3 with the next one. No, there will be 4 of the next one. I'm being bad again. 4 with the next one where we have only one of the 2 steps. You can have it from here to here, from here to here, here to here. And then finally, we have one more. We always just use the 1 step and just go all the way from 1 to 5. And I think we just add these up. The answer is 8. Unless I'm being, terrible, which I might be. Okay, I got it right. Thank God.
Yeah, that was a really nice approach. One alternate approach, which is very, very similar, but I would like to highlight for like slightly more complex problems of the same flavor, is you can do this with recursion. So essentially what you do is you notice that if you have a set of steps and you take 1 step or 2 steps at a time, then you can reach, for example, to get to 3, you can take all of the paths up to 1 and then go to 3, or you can take all of the paths to 2 and then go to 3. So what you're essentially doing is if we have some function like f sub k, where k is the kth step and fk is like the number of ways to get to step k, then to get to step fk, this is the same thing as adding the number of steps to k minus 1 and k minus 2. Oh, Skylar notes that this is like Fibonacci. Yeah, exactly. This is exactly how Fibonacci works. And so if you look at what Anshul did with calculating the first couple of steps, you'll see that we got 8, which is one of the Fibonacci numbers. So it's like a really cool way to approach this problem. But also because it's such a small case, you can also just like brute force all of the calculations. And this is much nicer in this case as well, because you're skipping one of the steps. So you have to be really careful with your recursion. All right. Oh, geometry. Okay. The figure shows a semicircle with center O. 2 of the angles are given. What is the size in degrees of angle? That says A, but I'm assuming it's alpha. Okay. How do we want to go about this? I guess most naturally what sticks out to me is that we have a lot of isosceles triangles. And this is because a lot of our triangles are comprising sides which are radii of the circle. And because the radii are all of the same, that means that we will get lots of isosceles triangles, which means lots of equal angles. Alex also points out lots of inscribed angles. This is true. That's a good observation. Like, for example, if we have that this is alpha, then by some inscribed angle theorem, we would have that this is 2 alpha because it circumscribes the same arc, but is from the center instead of this. Why is there a dot on the angle? That's a good question. I think this is meant to imply that it's a right angle. And this is interesting notation. I've not seen that before. But it makes sense why the dotted angle would be a right angle, because we have a triangle that is on the diameter. And since it's, on a circle and it's on the diameter, it circumscribes an angle that's 180 degrees. So the angle should be 90 degrees. So that makes sense. I think the game plan here is what I want to do is find this pink angle here. The reason I want to find the pink angle is because I know alpha plus the pink angle should be equal to 32 degrees. And the way to find this pink angle, I think the most direct approach is actually using Alex's observation about the special angle. And if we just find, I'll use a different color here. If we find this angle, then we can subtract it from 90 degrees to get the pink angle, and then we can use that to get alpha. So what we end up getting is that 32 equals alpha plus pink, and then pink equals 90 minus orange. It should get us our answer. Actually, we know what orange is because we have another isosceles triangle. If we look at the picture, then we can see that this triangle here is isosceles because it is 2 radii on another side. So what this means is that orange has the same angle measure as this bottom angle here, 67 degrees. Oh, this is the hard math. What is 90 minus 67? Pink is equal to 23 degrees. Thanks, chat. Very helpful. Okay. Oh, now this is not that bad because 32 is equal to alpha plus 23. Alpha equals 9? Why is arithmetic this difficult? I feel like it's 9. I see 9s in chat. Okay, thank you for supporting me, guys. Answer choice A. Nice.
All right, well, here's our next question. We have like a 3x3, and basically whenever we have like one of these 2x2 squares, we just add 1 in all the squares. So and then so the interesting thing is we have 47 in the center, and 47 is in like all of these pretty much, like in every single possible 2x2, like this one, the one at the bottom right corner, bottom left, and all of these. This always includes a center option. So we know that the number of like times we're like using like the 2x2 square is 47. And now the only time this 18, we'll start with the 13 actually. The only time this 13 will show up is that if we use this square, that's the only time, right? Any other square, it won't include this corner. So we know that this square occurs 13 times. Then we can do the top square of 18. This square will occur, and this plus this square. These top squares, if we add them together, we pretty much just get 18 times. So yeah, the middle number is 47. So we know that the total number of times we add is 47. So then we do 47, and then so we want to find out this corner, and this corner is just the other one. So basically, all the corners add up is equal to 47, and then the top corners is equal to 18 plus 13 plus x. Oh, I added times for some reason. Plus x. What is that? 47 is equal to 31 plus x. X is equal to 16. Unless I'm being, bad. I got it wrong. Shall see. Nope, I got it right.
Nice. I love how it's the arithmetic that's tripping us up. When you get to hard math, my calculus teacher said that like the hardest part of calculus is just like adding fractions. This is entirely correct. Fractions are so hard. Ooh, another step problem. Interesting. An ant climbs from C to A on path CA and then descends from A to B on the stairs, as shown in the diagram. What is the ratio of the lengths of the ascending and descending paths? Okay, I'm assuming when they say that the ant takes the stairs, the ant like does not stride between the stairs, but like traces the path of the stairs. At least that's my most reasonable assumption for an ant, but their ant is kind of big, so maybe it does stride. If it strides, we'll know from the answer choices that we're wrong. Okay, so I guess what this is asking us to find is what is the length of AC versus the length of this like entire step perimeter. And actually the cool thing about the steps is that we can kind of fold them in or fold them out. What I mean by this is suppose we were just to randomly take like an extension of this path into a right triangle. Then what we'll notice is that somehow this here lines up with this segment here, and then we can take this segment, this lines up perfectly here, and then we take this segment, and it goes here. And so we can take each one of these line segments and pop them out to complete the sides of a square. Now that's kind of cool because that means we don't have to do a bunch of different calculations to find the side lengths of each of the squares. You can just find this total path length when you go through this triangle. So that makes it slightly easier. Another good thing to notice is that the angles are kind of suspicious in this problem. Whenever you see a 75 degrees, that's a good indication that you want to split the 75 degrees up into two nicer angles, which are 45 and 30 degrees. And we see in this problem, that actually works. The reason this works is because we have the 60-degree angle down here. So we can drop an altitude. John says it's just a square. Yeah, exactly. It's really cool. Whenever you have these kind of, another like similar thing where this kind of pattern pops up is if you're asked for the perimeter of like a shape like this or something, you can similarly just pop out all of these angles to complete a rectangle and they'll have the same perimeter because you can just do the same like translating thing with the side lengths. Anyway, back to this problem. So now I guess we are looking for the ratio between two path lengths. So what this means is that we can assume some lengths, or we can assume at least one length to set our scale, and then whatever assumption we make, it'll cancel out in the fraction. So I guess my favorite thing to assume here would be I want to take this segment down here to be 1 because I want to avoid fractions. In that case, AC is going to be 2 because this is how trig works. I guess in a more satisfactory explanation, we can take this right triangle and reflect it over this perpendicular. And you'll notice that when we reflect it, we will end up with a equilateral triangle because we have 60 degrees and 60 degrees and another 60. And what this means is that this side length that we get when we reflect C over this perpendicular will be the same as AC. And so that gives us that because when we reflect it, we get 2, that gives AC is also equal to 2. Okay, and then we can just calculate these side lengths. Oh, well, this is like slightly trickier. I guess, well, the other thing that we have to use, which you kind of just have to know, is that this perpendicular will be root 3. Again, by trigonometry. If you want to avoid trigonometry, you can use, you can find the area of the equilateral triangle by using Pascal's theorem. And then from there, you can divide up by the base to find this height. And so we have that this height is root 3. And then we notice that when we split up this angle into 30 and 45 degrees, this angle over here will also be 45 degrees. And this is a right triangle. So what this means is that we can assign side length 3 here and side length root 3 here as well. So our total AB length is going to be 2 root 3. And our total AC length is going to be 2. So then what is the ratio of the lengths of the ascending and descending path? Well, it'll be 2 to 2 root 3, which is equal to root 3 over 3. And this will give us answer choice E.
So our next question is like a game where they play like word, and then if their word is like an original word and no one else has it, they get 3 points. If like 2 people have the same word, both of them get 1 point. And then if all three of them get it. They all get 0 points. So we have this person Sam who gets the least number of points at 19. And basically what we have to do first is like find a combination where he'll get 19 points. Like an easy way to do this is just by starting off by 30, like assuming that he gets all of the correct, right? Assuming that all of it's original, and then we can just subtract out the times when like either he has a matching word with someone else, or he has a matching word with the other two people. I can't speak. So then we have to minus 11 points somehow, and we need to split that between 2 points, because for every time he like goes from 3 to 1 point, he basically loses 2 points. If he goes from 3 to 3 points, he's basically like losing 3. So we need to make this in some combination of 2s and 3s. But also later in the question, we want to maximize James's score. So James's score, right? We want to have a maximum times where he doesn't have any overlap with anyone else. So first what we have to do is we want to maximize the 2s that Sam gets with the other boy. I don't know, whatever his name is. I didn't even tell you. So he'll have, I think, he'll have 2 more than him because he will have obviously 1 less matching because we know Sam has a least score. So in order to split up this 11 into parts, we will do 4 times 2, then we add the 3. I think that's 11. Hope it is. Okay, so we have 4 of these. So in order to just check our work, because I don't want to get this one wrong, then we have plus 5 times 3. That's 19. So that works out. So what we know is that Sam, the person with 19 points, got 4 questions matching with 1 other person, 1 question matching up with the 3 other people. I should put that as 0 actually, and 5 where he gets 3 points. Yeah, I had a brain freeze real quick. Now, what we do here, so basically the next dude James had to, no, so we need to find the dude with the middle score after this. So next we do the next person. So he will obviously, we need to just have 1 more of these because they can't have the same amount. So then we have 6 of these this time. Then we do 3 of these, and then 1 of these. So you'll have 2 more points than the person previously. So now we know that these people have 3 matching up together. So we have 1 more matching up on this category, and then 1 matching up on all categories. So now we do the 30 minus thing again, 30 minus 2 for the 1 overlap that we have left over from here. And then we do another minus 3 from the overlap from here. So then we do 30 minus 2 minus 3 equal to 25. I think. I don't know, this one's a low-key trippy problem. So let me check. Okay, I got it right. We're good.
That's a really nice approach. And you did the math correctly. That is even more impressive. All right. Problem 27. The 4x4 table, some cells must be painted black. The numbers next to and below the table show how many cells in that row or column must be black. How many ways can this table be painted? Okay, well, right away, there's some suspicious numbers. In particular, 0 is really, really suspicious. So I will just white out this row because we know that we will not have any in that row because we have 0. And then similarly in this column, we will also not have any shaded squares. So then, okay, looking at all of the other ones, I wonder if I should just casework this? I guess I'm not sure I see a better approach than just caseworking. So I guess what I mean by casework is I will just assume different things for this top row, and then I will work through all of the cases, and then we'll see how many we get. Okay, so I guess the first one, we can do these 2. So then what happens? So that means we will need some in this column here and some in this row here. So we can do, if we have one like this and one like that, that satisfies both that and that. And okay, we have found one arrangement that works. This is a lot of assumptions though. In particular, I assumed this, and then I assumed this. So I wonder if it is possible with fewer assumptions. Okay, in any case. Oh, I wonder if I can copy this grid and just have a lot of them. Oh, I have hacked. Oh, I see someone recognizes this problem. If you have a suggestion on how you can do it, you can also pitch it in chat. Okay, we can try to go for 5, and if we have more than 5, then this means there are more than 5, and that's the answer. All right, so we had something like this before. I wonder if there's another arrangement with using these two. So, okay, if there is something like this, then I think this also works. Because we have 2 here and 2 here. Yeah, okay. So this symmetric one also works. And then, let's see, is there another one? I think we have covered all bases with something like this. So now I will take this and put this one here and see if we have, okay, so now we've used up this row and this column. And then we need to have 2 in this row. But since we can't put anything here, that means that they have to go here and here. And I think this satisfies it. And we can also take the reflection of this image over this diagonal axis. And this should give us another symmetric, almost identical setup, which looks like this. So now it's either 5 or more than 5. So we need to find like 2 more for it to be more than 5. How possible is this? Let's see, can we take another one that looks like this? Okay, so I will suppose that these are all the ones with something in the top corner. So then I will just use these two. So we have to have 2 in this column as well, and since we can't have one here, that means that we will have 2 here as well. This is looking kind of symmetrical. It'll be unfortunate if it's symmetrical, because then it'll generate 2 instead of 1. Okay, and then we already have this used up and this used up. So, oh no, it's symmetric. Are there any other ways? Do all the 2 by 2 in the bottom right corner. Okay, let's try that. So you're suggesting all of the 2 by 2s in the bottom right corner. Oh, well, this one does not quite work because we are violating that there is only 1 here and 1 here. I think we've covered all of the cases because we've covered when we have a split like this, we've covered when there's a split like this, and we've also covered when there's 2 next to each other. And this one seems like it will not generate any more. This one already generated 2, and it seems like there's no other ways to arrange these ones. And if we move this one down here, then it seems like this one only generates 2 as well. So I feel like the answer should be D is equal to 5. Yeah.
I think we're on to the next problem. So this question is we're on 21 balls in a row, and they can either be green, red, yellow, or blue. And then we know that every like 5 consecutive balls, there will be exactly 1 red, 1 yellow, 1 blue. And then that gives you 2 greens in that 5 too. So we know that ball 2, ball 20, and ball 202 are all green. Now, like an interesting way to do that, if we think about that logically, like every like 5th ball, like so, like if like the first ball is like blue, that means the 6th ball has to be also blue, because when you think about this, like 5 here, right? Once we shift over from this one to the next one, we lose this blue, but we know there's also exactly 1 blue, right? So then you can only have this one as being a B, another blue, not a B actually. So if this one's blue, then that one has to be blue. So we know every 5th one has to be either blue or like whatever respectively. If this was green, that's a B, not an R. Green starts with a G. G, and that's a green. So basically we know that like every 5th one, we can do that. But now we also know that the position, okay, here. So now we can, if we just solve for 5 of these in a row, we can just continue the pattern, just solve them all out. So first, and then green obviously has 2, so it could depend. But I think we can just use from like the positions of them to depend. We can use like the modulus 5. It's like the remainder pretty much. So when we take the remainder 120, remainder 5, we get a 0, which is the last term pretty much, because 5 divided by 5 is also remainder 0. So that would be our first green one. Then also we have 2, which kind of a simple one. It's just the second one. And then we got the green one. And then finally we get another hint. So after any red ball, we have a yellow ball. And the only time we have that kind of 2 consecutive is like in this like 3-4 range. So we know that the after any red ball, the next ball is yellow. So after the red ball, we get the yellow. So the yellow's in that 4th position. And then we got this red in the 3rd position. And then that just leaves the blue in like, oh man, this is covering my face. And the blue in the 1st position, which we actually had initially. And then, so now we just take this remainder, 2021. That's just when we take the remainder 5, we get that first term, the B, or the blue actually. I don't know why I'm using B. It's actually letter D. But yeah, I think, hopefully, it is. It is blue.
Oh, that's so neat. It's a really elegant solution taking it mod 5. I believe that takes us to the end of our stream for today. That covers all of the questions. If you guys in chat have any questions for us, then feel free to send them. But this is all of the questions we are covering today. Bye, everyone. Thank you.
I'll see you guys.
Who looks like a turtle? Fascinating question.